We're gonna go ahead and get started. First, my name is Vyas. Thank you all for coming. This is Reinforcement Learning Part 1. This is a two-part lecture. The next one will be next week. So before I get going, just as always, please ask questions if there's anything I'm not explaining well, or if I'm going too fast, too slow, whatever. Just anything you're confused about. There's probably a lot of content in here that many of you are seeing for the first time. So whatever it is, just please ask questions. Yeah. So a good place to start is asking the general question, what is reinforcement learning, right? What does it entail? And the short answer to that is that it's a framework for solving a decision-based problem. This framework involves a few things. Firstly, an agent, which sequentially makes decisions in an environment. And the environment kind of provides the agent with like a framework. It provides the agent with states that the agent has to like understand. The agent takes actions to navigate between states. And the environment gives the agent a reward based on the action it took, potentially maybe the state it ended up at as well. So the agent will continue this process with the environment, taking actions, going to new states, receiving rewards, until it reaches what's called a terminal state, where it can't take any actions anymore. There's no actions available. So that terminal state, also called an end state, that whole process from the start state to the end state represents what's called an episode. And the goal of the agent is throughout an episode, its goal is to maximize the cumulative reward, also called the return. Okay. So there's some distinction between reinforcement learning and supervised learning. So the kind of generic regular machine learning, probably a lot of you are used to, and the kind that we've been presenting for most of our lectures. So supervised learning involves a predefined data set with established labels, right? Think like inputs and outputs. You provide a model with both, and it uses the output associated with each input to kind of learn and update its weights and biases as a result. There's no such concept of a predefined data set with reinforcement learning, right? Reinforcement learning involves learning by experience, where the agent learns by interacting with the environment and learning based on the feedback, the kind of rewards or punishments it gets, right? There's no established answers here. And that raises an interesting question. Could you use supervised learning to solve a reinforcement learning problem? Basically, could you train a model on states, actions, and their corresponding rewards and have it perform well? And it depends. Like, yeah, there's a whole field of machine learning devoted to that. But depending on the environment, depending on the setup you're working with, it could be harder. For example, you might need an almost exhaustive data set where if you don't know anything about the environment, you would need basically a lot of knowledge about the existing states that are available, actions that can be taken from each state, and the rewards you would expect to gain from that. That would need to be provided in some data set form, which you may or may not have access to. Additionally, rewards could be confusing. For example, a reward might not necessarily just be a number that's always the same whenever you take that specific action from a state. It could be a number sampled from some distribution where it changes every time. It's kind of hard to encode that in like a data set. So again, it just depends based on the kind of setup or environment you're working with. So let's take some time to really dive into what the environment would look like in a reinforcement learning problem. In most reinforcement learning problems, the environment is what's called a Markov decision process. And there's a few like, I guess, factors or a few properties that each Markov decision process has. First one is a state, as I just discussed. And that state is the basic situation that the agent will find itself in. The important thing to note is that in each state, that state will encode everything that's necessary for the agent to make a decision. So what that means is that the agent doesn't need to look at the previous states it potentially navigated in order to make a decision. The state that it's currently in should encode everything that the agent needs, and that's all the agent should use when making a decision or taking an action. These state spaces can be continuous or discrete, meaning they can be there can be a finite number of states or an infinite number of states. Today, we're going to assume a discrete state space, and next week, hopefully, we'll get into continuous state spaces. Similar to a state, we have actions, as I just discussed. Actions are choices available to the agent in each state. All the algorithms I'm going to go over involve a discrete action space, meaning that there's a finite number of actions you can take from a state. While it is possible to deal with a continuous action space, I'm just not going to go over that in the scope of the few lectures we have. Markov decision processes have a few more properties. First is a reward, as I just discussed. A reward is basically feedback given by the environment to the agent for taking a certain action A from some state S, right? We also finally have what's called a discount factor. A discount factor is just some coefficient that you would multiply future rewards by to weigh them less than current rewards. And it's usually something close to 1, like 0.99, 0.95. Let's go into an example of what this might look like. So let's say you've navigated across these states, right? From state 0 to state 1 to state 2 to state 3 to state 4. And you've received rewards by going through this navigation. Like from state 0 to state 1, you received a reward of 6. State 1 to state 2, you received a reward of 3, and so on and so forth. If you're generally computing the cumulative reward or the return, both terms are interchangeable, it would generally be 6 plus 3 plus 4 plus 7, right? That's your cumulative reward across the whole navigation, the whole episode. But by discounting, you're basically weighing the rest of the reward, rest of the cumulative reward, less than the current or the immediate reward. So look at what we have at the bottom. From state S0, we're basically weighing that state, from state S0, if we're discounting rewards by 0.95, our cumulative reward would not be 6 plus 3 plus 4 plus 7. The quantity 3 plus 4 plus 7 will be multiplied by 0.95, so it's weighed a little less, right? Does that make sense? Basically, what that's doing is it's telling the agent that any future rewards, the 3 plus 4 plus 7, is less important to it than the immediate reward that it gets, the immediate 6 that it receives. Similarly, we could apply this if we were calculating the return from the second state, or state S1 here, where the immediate reward it gets is 3, but the 0.95 is multiplied by 4 plus 7. So that return, that remaining reward is weighed a little less than what it normally would be. This discount factor is just something I want you to be aware of. It's something that'll show up in formulas. But for like the rest of the lecture, we're just going to assume a discount factor of 1. Yeah.
When you're going through your Markov decision process,
Mhm.
so are you already pre-computing your whole path through the episode? Because if you already know your future rewards, then
No,
are
you
gonna
don't.
take it those steps?
And that's something I'm going to get into when we actually get into the algorithms. The answer is you don't know any of that. When you're in, like, when you're mainly going to be computing the return when in the learning process. And as we'll see, based on this current setup, you only will know the return after you've gone through the whole episode. You're correct. So what an algorithm might do is it will go through the episode, store each of the states, actions, and rewards it sees. And then after the episode is done, it'll go back through them, compute the return, discount them if it wants to, and will then use that to update the associated one. Yeah, update them on. Does any other questions? Does this all make sense so far? Cool. So let's go into an example of what a Markov decision process or a general environment would look like. Let's say we have a 3x3 grid here, right? Where each dot represents a state that the agent could be in. And this state, as you can see, is just encoded by the current position it is on the grid. So we can just look at XY coordinates, right? The top left would be 0, 0. The top left would be 0, 0. Bottom right would be 2, 2. Does that kind of make sense? How we're just encoding the position as a state. So yeah, we can specify an initial state as 0, 0 and a terminal state as 2, 2. So in each episode, the agent's goal is to get from the top left to the bottom right. Does that make sense? How we can just we can say that and have that as like a goal? Cool. So similar, as you can probably imagine, in terms of navigation, the actions would be just cardinal directions, north, south, east, and west. So the agent would just be able to move, like either horizontally, vertically, whatever it is. We can add an additional constraint that the actions would only occur if the move is valid. So this is basically making sure that the agent isn't moving to a state that doesn't exist, right? If it's at the top left, there's no point. If the agent wants to move up, we shouldn't allow that, right? That's going to a state that doesn't exist. So we can just have it just not move at all and stay at 0, 0. We can also introduce rewards of -1 for each move that the agent takes. Yeah.
So in this hypothetical situation, would you also give a -1 reward for an invalid action?
Yeah, you could. Yeah, that's a great point. As I'm saying, if we introduce a -1 reward for every action, we're kind of motivating the agent to get from the start state to the end state as fast as possible. Can everyone see that? Because if we were to introduce, like, if we were to take unnecessary long paths like this one here, we end up with a cumulative reward or return of -6. Whereas a faster path or a better path would be something like this, right? Where you can't do any better. And this return, as we see, the best possible return to get from the start to the terminal state in this particular situation would be -4. So just to kind of finish up, the discount factor that I mentioned, we can just say gamma equals 1. So we're not doing any discounting at all. We're just computing the we're just computing the overall return or the cumulative reward as is, just as expected, each reward added to one another. Just to kind of summarize and also introduce some notation as to how I'm representing each of these kind of ideas. We're going to represent states using the lowercase letter s. And this notation up here basically means that each state comes from a larger set of all possible states, denoted by capital S. Okay, don't get like confused by that or anything. Similar with actions, each action is denoted by a lowercase letter a, and it could be taken from a larger set of all possible actions. And for the rewards, this is a little more interesting. We're going to represent a reward as a function of the state that the agent is currently at, the state that the agent will navigate to, S prime, and A, the action that the agent takes. So what this is saying is this function, the output of this function should be the reward the agent gets after moving to state S prime from state S by taking action A. Does everyone understand that? Cool. And then finally, discount factor. As I said, we're going to just assume it's 1, but it's going to be denoted by the letter gamma. And that's what we'll see in all equations and formulas that we'll have later in the presentation. And I'm going to point them out, so don't stress to like memorize that or anything. How's my pacing, by the way? Am I speaking too fast? Is it okay so far? Cool. Thank you. Cool. So that basically wraps up our discussion of what an environment would look like. Now let's kind of talk about how the agent would interact with that and what it would need to care about. And the first thing the agent might need to care about is what's called a policy. So a policy is a function that tells the agent what action to take based on the current state they're in, right? It's denoted by the letter pi, and it's again a function. So you input a state, and you'd expect to get the action that the agent should take. This is something that the agent will keep track of it, like, and hope to improve over like the training process. So there's 2 types of policies we can have: a deterministic policy, which is just a literal direct mapping between states and actions. An example of it is this, right? If you're at the gray, dot and you input the state you're in 2, 1, you would expect to get some action output, which could be move right. Right? Does that make sense? Cool. The alternate to that is what's called a stochastic policy, where each state maps to a probability distribution that you would then sample a particular action from. So there's no, direct mapping here. It's each action that could be taken from that state is given a certain probability that you would then, sample from as any other distribution. So to get to the equivalent of this in terms of like a deterministic policy would be having like one action have a probability of 1 and everything else having a probability of 0. Does that hopefully make a little more sense? Cool. Now recall our ultimate goal with reinforcement learning, and that's to maximize the cumulative reward, right? One direct way to do that is to come up with an optimal policy for that environment, because hopefully that policy, if it's optimal, it'll basically tell you exactly which move to make at any given situation. And if it's the best move, that's the one enabling you to maximize your cumulative reward, right? So just keep that in mind. So similar to a policy is something called a value. I'll refer to it as value function, value table. They all mean the same thing. And what a value is some function that describes the expected return of every state, right? So if we have this 3x3 grid here, this table to the right represents the expected return of any given state, right? So let's look at this, this top left dot, the blue dot, right? The expected return that we would expect if we were positioned at that state would be -4. Recall that each action we take has a reward of -1, right? So if we were at the blue dot, the best way to get to the goal, however good it is, the best possible way would still incur a return of -4, right? Because there's 4 actions that you would need to get to the green dot. Does that make sense? So that's what the value represents, the value function represents. Note that what I'm describing here is the optimal value function, where it accurately describes perfectly best case how to get the best way to get from the start to the goal. And this is, again, similar to the policy, something we would hope to improve. If an algorithm is, as we'll see, value-based, it'll hope to improve this value function so that it's as accurate and describes the best possible result from any state. Similar to a value function is a Q value function, which takes it basically another step, right? A Q value function is some function that describes the expected return of taking action A from state S. So if the value described the expected return of state S generally, the Q value takes it a step further and says, what's the expected return if you're at state S and took action A? So let's take a look at like what this might look like. So if you're at this blue dot again, this is what an optimal Q function would look like for this particular state, right? If for the action of moving upwards, we would expect a return of -5, right? Because you would move up, and then because it's an invalid action, you would stay there, incurring a reward of -1, and then move to take 4 actions to get to the end, right? Similar with here, moving right. If we moved right, we're incurring a reward of -1, and then -1, -1, -1. Similarly, this is what's called an optimal Q function, and it's the same idea as the value function. This is something that an algorithm might hope to find. So let's look at both of these side by side. Hopefully you can see that they're pretty similar. But if you take a closer look, what do you actually notice? You notice that the value of a state is equal to the maximum of the Q value associated with that state across any possible action. And that should hopefully make sense, right? If the value function is accurately describing the best possible return you could get from that state, that should be like generalized across all actions that you could take, right? This should hopefully make intuitive sense to you. Any questions or? Cool. So similar to that, we've gone over values and policies. You should hopefully see that those are also somewhat intuitively related, right? Because if you have some sort of optimal value function, you should be able to derive a policy from that, because the policy would hopefully move you in directions of states that have higher values, right? To ultimately maximize your cumulative reward, you want to travel across states that have higher expectations of future cumulative rewards, right? And that's what the value function describes. So a policy should be innately related to that. To be more accurate, we can just see here, the best action for some state S corresponds to the action that has the largest Q value. It's the same relation I just talked about in the previous slide. And this relation is actually interesting to us because it gives us 2 approaches to find the optimal policy. As I said, that's our kind of indirect goal at getting at maximizing the cumulative reward. So to find the optimal policy, one way we could do that is by starting with a random policy, or a policy where each action is given equal weight, and just iteratively improving it, right? So if this is what your policy looked like, pi of S, if it started like this, where each action is given equal probability, ideally over some training process, we could hope to improve it and get something representing something like a deterministic policy, so that we could just easily, really quickly see, okay, since this action has, if we were to sample from this, right, the only action that would come up would be action 0, corresponding to index 0, which could be moving north, right? That's one way. Another way we could hope to find an optimal policy would be to find an optimal Q value function and converting that to a policy in the way that I just described. If we have some Q value function, so if this basically describes the Q value for every action from a particular state, you could then just take the argmax of that, find the action with the largest Q value, and assume that have your policy direct you towards that. Yeah.
What does like the colon represent?
Yeah.
That's almost-
Sorry, so this is like, I tried to like mimic like Python notation. So a Q value basically takes in 2 parameters, right? The state and the action. Whereas a value takes in 1 parameter, just the state. So I wanted a way to represent like all possible Q values for a particular state. So this is basically what this means. Like, remember the square that we had a few slides ago, this guy? It's basically that represented in like array form. So the general idea here is that if these are your Q values associated with some particular state S, you'd want to move in the direction of the largest Q value. And that would be -1, right? So that's what ideally your policy would say. And that makes intuitive sense because they're intuitively related. Does that make sense to everyone? Cool. So what I basically described are 2 fundamental, I guess, kind of methodologies that we can direct our focus to developing an algorithm for. We have policy-based, where we hope to find a policy directly by, just the first approach, starting with a random policy and iteratively improving it. Or we can do something called value-based, where we try to find an optimal Q value function and later convert that to a policy when making decisions. So today we're going to focus on value-based methods. Any questions about anything so far? It all makes sense. Nice. Okay, so let's first go over what a generic value-based algorithm would look like. Okay? Let's say we're navigating in our same 3x3, exact same 3x3 environment, exact same reward structure, exact same actions. Okay? So let's say we've taken these two actions and we're currently at the gray dot and we've taken two actions resulting in two -1 rewards, right? Let's say this is what our Q value function, our Q value table looks like. Notice how it's not the optimal one as we saw here. Like, let's say we've done some training and it's got to this stage and we want to keep improving it. So as I just said, we're going to navigate through a Markov decision process, through an environment from the start state. And then from each state, as I said, we're taking an action and receiving a reward. Notice when I say taking an action, right? We don't have any way to do that. And that's something I'm going to get to. So for now, just assume that we have some way to take an action somewhat intelligently that we can then use to receive a reward from the environment. Okay, based on this action and this reward, we then want to update our Q value estimates. Now, when I say update Q value estimates, that's another thing I'm kind of hand waving. Assume we have some way to do that. We can either do that at the end of the episode, so when we reach the goal, or we can do that at the end of each step, so after we reached our reward. Those are two fundamentally different ways that I'm going to get into in a few minutes. But the idea is that you would be updating your Q value estimates throughout somehow. And then, as I said before, we would stop when we reach a terminal state because we have no more actions to take, and that represents an episode. So the idea is that you would be updating your Q value estimates in some strategic fashion throughout across over multiple episodes for an extended period of time, and hopefully you'll converge to the optimal Q value function, the Q value table for that environment. Yeah.
So in this case, where you have like multiple Q values that are the same, would you just like randomly pick from among those actions?
Yeah, that's one strategy. Yeah, it's perfectly valid. And yeah, recall our goal, right? To get to know what the maximum possible cumulative reward is, we want to get our agent to navigate a trajectory that results in that, right? So when we're picking actions or updating Q value estimates, we're hopefully getting to this goal. Just something to keep in mind. So as I just said, how do we pick an action, right? We're doing value-based reinforcement learning, right? We're dealing with value functions, Q value functions. How do we pick an action, right? Because an action is picked by a policy. So there's two ends of the spectrum here when you're picking an action. And one end is that we always pick a random action. Regardless of whatever state you're in, regardless of whatever your Q value table looks like, just always take a completely random action, right? And there are some positive attributes to this strategy, mainly that you're able, by taking a random action every time, over time, you will have probably revisited every single state and taken every single action, right? That's just the nature of always taking a random action for how many ever 10, 100,000 times. But the problem with this is that the agent will never navigate the most optimal path, even if you take random actions. Because just think about it, for the agent to navigate the most optimal path, it needs to make the right move maybe 4, 5, 6, 7, 8 times in a row, right? And that's for a simple example. If we're taking a random action every time, that just won't happen just based on probability. So the exploration part of this is good, where we want to visit every state, get an idea of what every single state or action looks like, but the rest of it is not. The other end of the spectrum would be always picking the action with the largest Q value. This is a greedy approach. If we always pick the action that we've seen is really good, we're intelligently picking actions, right? We're intelligently moving in a way that we know is relatively good. But there is a problem with this approach as well. And the best way to illustrate that is to look at this example. Same 3x3 grid world, but let's say you introduce a reward of +1 for every move instead of -1. What this is motivating is the agent to stay on the grid as long as possible. Does that make sense to everyone? Why a reward of +1 motivates that? Cool. And okay, now that everyone understands that, let's assume that this is our very first go, right? We've initialized all our Q value estimates to 0 just to start off. And our agent has navigated one path, right? It's gone from this blue dot across these arrows down and just navigated this path until it reached the goal. And it correspondingly updated its Q values, right? For this, from the start state, we got a return of +6, right? Because we had 6 + 1 rewards. So that's what we updated our Q value with here. Similarly here, from this state, we had a return of 5. From here, we had a return of 4, and so on and so on. Right? Does everyone understand how these Q values got updated? It seems pretty intuitive so far. However, let's say we try to navigate an environment according to this action picking strategy. Again, assuming we had Q values that looked like this, right? We would go from the start, move in direction of the 6, so move here, move in the direction of the 5, move in the direction of the 4, move in the direction of the 3, move in the direction of the 2, and move in the direction of 1. But that's just revisiting the same exact path we just saw before. The agent isn't exploring anything here. A better strategy that would result in a higher cumulative reward would be moving from this state to this state, right? You guys can see that, right? Moving from here and then coming back and looping around. That would result in 3 more +1 rewards. But since the Q value here is 0 and this guy is 2, the agent will always go in the direction of the 2 Q value. So as such, it's never going to explore any potentially better paths. And that's the fundamental problem with this strategy. It's gonna if it finds a good path, it's gonna keep doing that and never explore any potentially better ones. So we've seen both sides of the spectrum. We ideally want something in the middle. And this problem, this kind of dilemma we're dealing with, is called exploration versus exploitation. This is a pretty common dilemma across reinforcement learning in general. And it basically means, like, in our action picking strategy, we want to thoroughly exploit promising paths and really see how good they are. But simultaneously, we want to also explore a wide range of paths, potentially paths that might be worse, because we've not explored it as much, but we want to keep exploring it just to see if there could be something better. Does that make sense overall? Cool. So one very simple action selection strategy that does this is what's called epsilon greedy. And the basic intuition is this: at any given state, you will either select the action with the largest Q value, so that second strategy I went over, or you will select a completely random action, the first strategy I went over. And whether you select either action is governed by this value we have, epsilon. Basically, with probability of epsilon, you will select a random action, and with probability of 1 minus epsilon, you will select the action with the largest Q value. Let me explain this, or let me make this clearer with an example, right? Let's say we have epsilon of 0.1 and we're at the blue dot, and this is what our Q values look like, right? Basically, let's say we have a random number generator to simulate a random occurrence, right? If our epsilon is 0.1, that means that a random number generated between 11 and 100 will correspond with this phase, the 1 minus epsilon phase. Whereas a random number generated between 1 and 10 will correspond with the top phase, the epsilon phase. Does everyone understand that? Cool. So let's say our random number generator comes up with some number between 11 and 100, right? That means that we want to select the action with the largest Q value. So this, given our current Q value or our current Q table, is going to be the action of moving to the right. See, because this is -3, it's our largest Q value so far. So here we're going to follow the greedy choice of picking the largest Q value we've seen so far. If the random number generator came up with something between 1 and 10, we would instead pick a completely random action. Has nothing to do with our Q table. It will be completely random, where every action is given equal probability. So this could be any single action that's being picked. Does everyone understand this strategy? Basically, the main idea is that most of the time, epsilon greedy will pick the action according to the Q table. It'll greedily pick the best action so far in the Q table. But sometimes, maybe 10% of the time in this case, it'll pick a random action. So it still gets the chance to explore paths that potentially would never be explored otherwise. Does that make sense, this general strategy? Cool. So that solves the problem of picking an action. But then another thing I kind of hand-waved was, how do we actually update Q values, right? I said we could update them at the end of the episode. I said we could update them during, but how do we actually update Q values in an intelligent and stable way? And we can actually derive a kind of update rule that we can call that if we just run it, it'll update the Q value. We can actually derive one. So let's just go ahead and derive one. This part will be a little math heavy, but I don't want you to really memorize the formulas that are going on, just generally understand the intuition. Okay, let's get into it. So intuitively, right, before we begin, the Q value of a particular state and action is going to be the average return obtained by taking that action A from state S, right? If we've gone through some Q value effectively, if we're at some state S and taken some action, if we've done that multiple times over multiple episodes, we want our Q value to be representative of all of that in some kind of average, right? Does that make sense? How a Q value is just an average across all cumulative rewards, all returns that we've got. Cool. So with that, we can just write generally a formula for the Q value of some particular state action pair as this, right? If we have G representing each possible return, right? And we've basically updated this n times, that means we have that means you have n associated returns, n G's basically for that Q value. So this is just generally what the formula for the average would look like. Okay. Let's just rewrite this. So we added a sub n to the Q value notation just to indicate how many times that value has been updated. Okay. The idea is that we want some way to express this recursively. So we can just say like new value equals old value plus something, something, something. Okay. So now that we have this, I'm gonna just ask you to trust me that that these two equations are exactly identical. There's like 10 steps of math that makes it work that I just didn't include because it didn't seem like super necessary. But yeah, just trust me that these two equations are exactly identical. But what I don't want you to memorize this formula, the second equation we have here, but I want you to understand what it's saying. And it's basically saying that the new Q value for state S in action A is equal to the old value plus some step size times the quantity target or the latest return that was gained, basically, minus the old value. Okay. So that's just the general form that our update rule is going to take. So there's a few missing pieces here. But does everyone understand generally this this form? It'll make a little more sense as I go throughout the rest of the lecture. Yeah. Target, that's basically the latest return we got. So if we're sorry, so recall how I said if a Q value is updated like 10, 15 times, that means that across how many ever episodes it was trained on, that 10 or 15 returns kind of went through that Q value, meaning the agent went through a trajectory that at some point was at state S, and then the agent immediately took that action A. Does that make sense? That's what target is, basically. It's the most recent return. Yeah. Any other questions? Okay, cool. So this is the exact same form, but I want to pay attention to the step size, 1 over n. Okay. Basically, what we're going to do is instead of having 1 over n as our step size, we're going to sub out that for some parameter alpha. Basically, does anyone know why we'd want to do this? Basically, we'd want to do this so our agent can keep learning all the time. Imagine if we have 1 over n, right? If we have 1 over n, and like n gets exponentially large, it gets like 10,000, 100,000, a million, whatever it is. Like 1 over n, 1 over that quantity is going to be like minusculely small. So whatever the Q value is at that point, it won't ever get updated again because that quantity that this target minus old value becomes, it's going to effectively become 0. So our Q value will never get updated again. So that's why we want something like alpha. It's where our agent will keep learning throughout, right? Think of alpha like a learning rate in traditional machine learning, right? That's something that you can tune. That's a parameter that you can pick. And yes, if you wanted to, you could set up a schedule where the learning rate decays over the number of epochs. So we could do something similar here. So it gets to a similar behavior as 1 over n. However, to get more general, we're going to sub it out with some parameter alpha. Cool. Finally, we're almost done. We're going to go from this update rule to this by just taking out the subscripts. So our form just now becomes Q new value equals old value plus alpha times the most recent return G minus the old value. Okay. So this is basically our update rule. We can use this in algorithms, as we'll see going forward. And hopefully the parts of, and I know it probably doesn't make a lot of intuitive sense right now what this formula is doing, but it will hopefully after we see the first example. And yeah, just a quick note, moving forward, we're going to assume that alpha equals 0.1. So before we go on to the example, notice that this update rule requires knowledge of what G is, right? As you brought up earlier on in the lecture, we only know G after we go through an episode, right? We only after we go through the episode will we know what the final cumulative reward of that episode is. So only then can we update our Q values. So is there a better way to do this? Yes, potentially, but the original way of only updating the Q values after an episode is actually a perfectly valid algorithm. And this algorithm is called Monte Carlo learning, where, as I just said, we're going to navigate an entire episode to compute the actual cumulative reward for every single state that was visited through the episode. Any questions so far on anything before we proceed? Cool. So let's walk through an example of what a Monte Carlo reinforcement algorithm would look like. Basically, as I just said, we're going to follow an entire episode and store each of the states, actions, and corresponding rewards along the way, right? And let's say we've gone through this path, right? And these are the states we've stored. Like first, for example, we started at state 0, 0, took action E and got a corresponding reward of -1. We were at state 0, 1, took action E as in like east, moving to the east, got a corresponding reward of -1. From here, we took action south, like moving south, reward of -1, and so on, right? This makes sense. And this is what our Q table would look like. This is our very first time. We haven't made any actual updates yet. Does this make sense though? Nice. So before we do anything, we're gonna compute what G would look like, what the return would look like from each state's perspective, right? From this state, right, the return is gonna be just the -1. Why won't it be -4? Because that's the actual return. It's because these previous states didn't like they don't get involved. Yeah.
So is this where if you were using like a discount rate, this is where it would like show up?
Yes. Yeah. This is where it would show up. Exactly. But yeah, as I said, each state, right? It's part of the Markov, one of the properties of the Markov decision process. It only matters to the agent the current state it's in, right? So any reward it got until then should not matter at all to that current state. Does that make intuitive sense? And also should hopefully explain why these returns are structured like this. Nice. So now that we have our returns, let's just use this exact same update rule that we derived a few slides ago. Let's use that exactly to update each corresponding Q value, right? So we're going to first go with this state, right? Our most recent state in our trajectory. The corresponding return G was -1, as I just talked about. So this is what our formula would look like, right? The old Q value used to be 0, right? The alpha is 0.1, as I said before. G is -1, and the old Q value again is 0. So just by following this exact formula, we get what our new estimate of the Q value should be. And that is -0.1. Does that make sense how I got there? Because that's basically the gist of this algorithm. We would just basically do that for every single every single state that we visited in each episode. Notice how the value of G is different for this state because we're talking about this state here, and we would just keep proceeding like that. Yeah. So this is literally it. This is what an update would look like for the Monte Carlo algorithm. And the idea is that you would hopefully keep repeating this upon episode upon episode upon episode until hopefully the model improves and yeah, you get something resembling what the optimal Q value function would look like. Yeah.
Is alpha remain the same for every episode, or can it change?
Sorry?
Does alpha remain the same for every episode?
Yeah, it can. I just said 0.1 just for the sake of the lecture. But yeah, that's something you would pick, just like a learning rate in regular machine learning. Alpha is something you would pick. If you wanted to, you could have it decay over the number of episodes you train. But that's like the programmer's choice. Any other questions? That's a good question. Cool. So, yeah, hopefully, as you keep doing this, and as for any general, reinforcement learning algorithm, the Q table will converge to the optimal one. And the way you can know when this happens is when the update rule doesn't modify any Q values. So let's take a look at this quantity, target minus old value, right? If the old value gets close to what target actually is, this quantity gets close to 0. Does everyone understand that? So when this quantity gets close to 0, the formula then becomes new value equals old value plus 0. So new value equals old value. So what I'm trying to say is that as your Q estimates get more and more and more accurate, as you get closer and closer to the actual reward you're getting, they won't really update much anymore. So that's a good sign that you're doing something right. Your model is learning, or sorry, your agent is learning. That's when your Q table becomes more and more and more accurate. Does that intuition make sense? Hopefully this formula makes a little more sense. Nice. So yeah, this is a pretty straightforward algorithm, hopefully. Are there any problems with this? And yeah, there's a few. The main thing is that, as you just saw, the updates only happen at the end of the episode. What does this mean? It can generally mean that learning is slower, right? Because you're only performing updates at the end of each episode. If there's something that the agent learned like mid-episode, that's only getting updated at the end. So that's generally a little slower than if we were to make updates. If we were to make updates like throughout the episode. Because if we made updates throughout the episode after each step, if we made updates throughout the episode at each step, the agent might learn something it could apply later on in the episode. But here it can't because it only happens at the end. That's one problem. The other issue with Monte Carlo reinforcement learning is that it's generally a little higher variance. And what I mean by that is that it uses the actual return that's gained by navigating through the environment. Let's say we're navigating through the environment and on one go, we got a return of -5, right? But on the next go, we got a return of minus like 20. Both of those returns have to get propagated and updated to each of the states that it went through. But they're both completely like different values, and they both could correspond to different updates. One update would be more significant than the other, and so forth, right? So that's what I mean by higher variance. The updates rely a lot on what you're actually getting, and that makes it a little more unstable. Does that make some sense? Okay, cool. So that problem is directly solved by a different kind of algorithm that instead of actually using the actual return estimated or calculated at the end of the episode, it estimates the return midway. So it's able to perform updates mid episode. And this form of reinforcement learning is called temporal difference learning. And it basically uses a recursive formula to compute G to estimate the return. And this formula is this. This formula is basically saying that the return that you should get, the expected return should be the immediate reward you get by moving from state S to state S prime, plus the expected return of state S prime. Does that definition make sense? Basically, G is the same thing as the value of state S, right? We're just saying the value of state S is equal to the immediate reward you get by moving from state S to state S prime, added to the value of state S prime, right? If you have a bunch of rewards just all added together, this is basically subdividing them into the immediate reward, the very first reward that you got, plus the rest of the rewards. Does this idea make sense? Cool. And yeah, I have the discount factor here. As I said, this is, we're just going to assume it's 1, so the computation remains straightforward. So just to kind of reiterate why this is good, basically, we're updating Q values based on expected returns, not the actual returns that I get. So it's less susceptible to environments with seriously high variance. As an example, think about like the problem where you're training a self-driving car to come to a stop. It'll say it's moving at like 30 miles an hour. You're training it to come to a stop. Let's say your reward structure is such that it's like maximizes the comfort of the person in the car. So something like just going like full brake and stopping immediately, that would not be great, right? It's just a hypothetical environment. If you were training a Monte Carlo algorithm on this, you would only update Q values after the car comes to a complete stop from 30 miles an hour, because that signifies an episode, right? But what if during that episode, the during one sequence, the model or the agent completely messed up and did a completely terrible brake application? That completely terrible brake application, that's hopefully the anomaly, that's going to get represented in the overall return. That's going to get represented in the overall G, and that'll get propagated to the relevant states. However, in TD, that won't really have much of an impact, because the Q values, since the Q values are updated with each individual brake application, it's using the expected brake application of future time steps in order to estimate what the rest of the episode would look like. So it won't really get impacted by any outlier situations that could include, braking horribly. Yeah.
So is there would you usually limit how many steps into the future you're looking, or is this I'm just thinking would this be a really expensive recursive algorithm? You're just
That's a good question. Usually for the scope of this lecture, we're only looking one step. So we
Okay.
use the immediate reward and then the estimated reward of future states. But it's not an expensive operation in that, because we're storing the Q value for every possible state in action, right? So as we'll see, we can just literally use those in place of
so you
VMS
don't
prime.
you don't really need to calculate forward so much as you use what's already stored there. for
Exactly.
the future.
You
Okay.
use what's
Yeah.
already stored there, and then ideally your Q values will learn together.
Okay.
Yeah.
What is like predicts what the future values may be?
It's because we're storing the Q values, or just generally the value estimates. We're just storing that of future states. Like if you look at our, let me try to find an example. Like this, for example, right? If we're at state 0 or 0,0, that update rule, reward plus the future estimate, that would be like the rewards you gain from moving to this state, plus the estimated return for this state. So I don't have a better example or a better visual. Does that make sense though?
Like, what's it called?
Yeah, great question. So yeah, with these higher up states, higher up as in more steps to the end, it won't initially. However, these guys, they're only going to be reward plus whatever's here, right? So it's only going to be reward because these guys will never change because they're at the terminal state. So hopefully these guys change, and then it eventually gets propagated up all the way through, and hopefully, and yeah, it will get to the start state. Does that make sense? Yeah, really good question. Any other questions? Nice. Okay. So let's look at what a general update rule would look like for TD, right? Recall our formula, right? We can literally just make a direct substitution for what G is in this previous formula. So that's what we're doing. If this is the general formula that we derived and we're using in Monte Carlo reinforcement learning, we can literally substitute that with our expected return instead of our actual return. So this general formula would work for any TD-based algorithm. Does this make sense? Nice. So that raises an interesting question, right? Recall that we're only using Q values, right? But this guy involves the value of state S prime. So how do we substitute that for a Q value? And we actually know the answer to this. Do you recall how earlier in the lecture I brought up that the value of a particular state is equal to the maximum Q value associated with that state across all actions, right? We can literally just use that exact rule in place. So we can do a direct substitution of that into what V of S prime should be, right? This max, whatever, all of that is just saying that if you're at state S prime, right, this is just returning the maximum Q value of all actions A prime that could be taken from state S prime, or the maximum return that you would expect, right? And we know based on earlier in the lecture that this is equivalent to the value of state S prime. Any questions? Does anyone need clarification about this substitution? Nice. Okay. So this update rule that we just found here, if we use the algorithm that uses this update rule is called Q learning. Before we get into an example of what Q-learning would look like, let me just go over, just reiterate the differences between Monte Carlo and Q-learning. As I just said, Monte Carlo, it just uses the same exact update rule that we derived, using the definition of an average Q value. And it can only be updated at the end of an episode, once we have the actual return, the actual cumulative reward. Whereas with Q-learning, we're estimating the cumulative reward using the immediate reward plus the estimate of the return of the next state that we end up at, right? With Q-learning, this estimate basically allows us to make updates after every state, as we'll see. Everyone understand the distinction? Nice. So let's go, kind of short on time. Let's go over an example of what a Q-learning algorithm would look like. Basically, let's assume we're following an entire episode, right? We're starting at the blue dot, right? State 0, 0, right? And this is represented by these Q values, right? These Q values, like, let's say again, we're like mid-update. We've done like 1,000 episodes, and this is what our Q table looks like, okay? These blue ones, I've just highlighted it blue just because that's the one I want. These are the ones of interest, basically. Okay, so we're starting in the green square, right? That's our current state. And we're going to take an action according to the epsilon greedy policy, right? And that will enable us to receive a reward from the environment. Recall what the epsilon greedy policy is, right? We're just in epsilon greedy. It basically says that most of the time, we're going to take an action that corresponds with the best Q value. But sometimes we're going to take an action that corresponds to some random action. Yeah, sometimes we're going to take a random action. Most of the time, we're going to take the action that corresponds to the best Q value. In this case, you'll notice we're taking a random action, right? Just based on what the Q values look like. So, but this orange square, this is going to be our state S prime. This is the state we end up at after taking the action. Everyone good so far? Okay, so now we have to figure out A prime. This is going to be, recall, the maximum Q value from state S prime. And that is going to be this guy, the -5. So this triangle here, this is going to be our Q of S prime A prime. This is what we're going to use to estimate the return. So to estimate the return, it's basically going to be the reward you got from moving from this state to this state, so -1, plus the return of, plus Q of S prime A prime. So this is basically saying, okay, we have a reward of -1, and then the rest of the return is expected to be -5. So our overall return that we would expect is -6, right? It may not necessarily be the case. We don't know because we're not waiting until the end to do it. But this is what we're estimating based on the Q values we know. Does that make sense? Okay. So now we can just use this Q value update rule. It's the exact same one that was defined earlier. Yeah. Sorry? Oh, it's because we will. Sorry, I was just saying that that's the return we're estimating, but in our actual update rule, we will add it. Yeah. So yeah, exactly. We're to update our Q value of this state, right? This is the action we took from the first state as 0. This is what we're just gonna do the math, basically. The value used to be -7, exactly, plus alpha 0.1 times the reward of -1 plus gamma of 1 times what the Q of S prime A prime is, so -5, subtracted from the initial Q value. So this guy used to be -7. So this is what this formula comes out to be. And if we do it out, we get -6.9 as our new estimate for this particular Q value. Does that make sense? Is everyone good with that? Okay, cool. Yeah. And that you basically just repeat that for every single state, for every single stop, every single step throughout an episode. And then you repeat that over multiple episodes until, again, hopefully you get to something resembling the optimal Q value function. Does that make sense? The only difference between Q-learning and our Monte Carlo algorithm is the update rule. We make our updates after every step, and we're able to do that because we have a way to somewhat stably represent the estimated return. We don't need to wait until we have the actual return to make an update. Make sense? Cool. So just to kind of reiterate where we are, what we've kind of explored, within the field of RL, we saw we have two methods, policy-based and value-based. And those are different ways at getting at the optimal policy, which we can use to make decisions. Within our exploration of value-based algorithms, we went over Monte Carlo, which uses the actual return that was computed by going through an entire episode and then iteratively going back and updating Q values. And then we have Q learning, which is where we're able to estimate the return instead of getting the actual return and make updates after every step. So we've done all of this, right? But there's still a very fundamental flaw with all of the algorithms we've just gone over. And that is, can any of the algorithms we went over, Monte Carlo or Q learning, can any of them deal with continuous state spaces? Meaning like an infinite number of states, like think like decimal values instead of just, a nice discrete finite number of states? The answer is no. Can anyone tell me why though? Yeah.
You have the updated infinite number of states.
Exactly. That's literally it. We're storing Q values for every single state and action that's possible. If we're dealing with a continuous state space, that means we have to deal with an infinite number of states, right? How is an algorithm gonna store Q values for an infinite number of states? It can't, right? There's just no way it can. So right out of the box, neither Q learning nor our Monte Carlo algorithm will be able to work as soon as we scale up to a continuous state space. But we can modify our algorithms to be able to do that. One way we can do that is by grouping our states into something like bins, where we would just assume a discrete state space. So look at this line, right? And let's just assume that was like your like continuous line of what the state could look like. But by bin, I mean that you would just, partition this part of the line and just basically partition the line off into segments that you would then, you would then have a finite number of segments that you could then train your algorithm on, because if you're training it on a finite number of bins, it could work. Does everyone understand how this would work? Yeah. But there is the potential problem that you're oversimplifying your state space. Doing this implies that you know how your states generalize with one another. If state -1.1 and -1.2 are similar, binning them like between like -1 to -2 would probably work. But if they mean completely different things and you put them in the same bin, the algorithm is not going to perform well, right? Because you're giving it faulty information, right? That's just a fundamental flaw of doing bins across like anything, not just reinforcement learning. You run the risk of oversimplifying your state space. What you could do instead is use something like a neural network to estimate Q values. And you would basically use this instead of that Q table that I had, you would just use this and train it using more supervised learning techniques. And as it turns out, we can actually use a neural network for more than this in other algorithms that hopefully we'll get to. But just to estimate Q values, think of like just some traditional neural network, 2 inputs where you input the state you're in and the action that you hope to take, right? And for a neural network, the inputs could be continuous, right? So could the output. The output could then be your Q value estimate that you would ideally train in some supervised learning way that makes sense. And there's actually an algorithm that does this directly for Q learning called deep Q networks that we're gonna hopefully get to next week. But that about wraps it up for this week. Thank you for coming.